It started now.
Okay, as we started recording, and I think, Vince, you can talk with Adam. I know him also for 30 years, maybe more, 50 years, no, Adam? You know, it's us, we spend in the same base. But anyway, you can start, ask the question. And
one who I worked with when I was there.
Oh, yeah. Yes, I think I know him. Yeah. Okay.
Perfect.
So, let me spend a minute to describe how I'm connected with this project, and then you can ask whatever questions you want. So, I've worked with Ofer for many years, and in many positions at the Technion, starting at the beginning of his project. And we've just concluded an agreement with the electrical engineering department that officially takes a position of oversight over the projects that he's doing in high schools, as a signal to the Ministry of Education that the level of what they're doing is high enough so that they actually get credit when they get to our department. It's very similar to advanced placement in high schools in the United States, where there are programs that if you take this, then you are exempt and you get credit at the university for the work you have done. And we do that in two places. One is a project, and another one is lab work. In our department, there are requirements for lab work that are part of the curriculum. And the introductory laboratory, which introduces you to measurements and instruments, and is the basis for later work, we recognize what is done through the tools that Ofer has developed, and also the lab in physics, which I think is much more interesting, because that is a very serious change of concept. Rather than deal with a standard laboratory, you work through instrumentation which is completely integrated with computing, and it changes both the perspective and what you can do. And it also changes the way students perceive what they're doing, because it feels to them like this is something which is much more connected to their experience. They work with interfaces that they're used to, that look modern and look relevant, and also look like they could use them to do a lot of stuff that would be of interest, as compared to standard laboratories where things look like they come from different planets. So I think maybe the most important point is that this is a very advanced and sophisticated platform. It was built on a very modern technology with an interface which I think is fairly intuitive. So like most interfaces on computers, it's graphics based and allows handling basically any data that you collect, but also the collection of a lot of data, and processing and presentation of data. And in that way encourages students to understand the relations between the different data points that they're collecting, which are described by mathematics and physics and everything else that they're studying either in high school or at the university.
And is the underlying software LabVIEW based, or is it something else?
Yes.
It's LabVIEW based, but there is a very large layer on top of it.
Mm-hmm.
Yeah, so LabVIEW is, so I think one of the principles that Ofer uses extensively is the principle of lazy people, which is you don't recreate the wheel because it's already there, but you utilize. So at the heart of everything is the smartphone that is a wonderful platform to collect data. And the observation that you can use this to collect data is very simple, but it really changes everything. In high schools, if you want to allow the students to measure acceleration and you go and buy the instruments that are required for that, it really stresses the high school budget. It requires people to operate equipment that is at the edge of what they can do. And it requires teaching people to use instruments. And so there's a lot of overhead to the experiment. Once you look at the smartphone as a data collection instrument, everything changes because everything becomes very familiar and very easy and with almost zero budget.
And the software allows access to all of the sensors. That's sort of the magic here.
Yeah.
So
So
I don't have to dig into this. You've taken
so
care
has
of it.
an advantage that not only does he have access to things that you can do if you knew how to program, but he actually talks to the people that write the software for the phone to convince them to allow him access like a very serious developer. So what they allow developers is more than they allow the consumers. And so he gets access to very detailed data. Anything that a smartphone can measure, he can get out of it.
Is there an ability to connect a different kind of sensor to the smartphone, let's say via one of the ports, maybe the microphone port, to get other information, like something that it couldn't already measure?
Yes, it's also an IoT device. So the idea, we have a sensor through the phone himself, through the smartphone himself, like accelerometer, gyro, GPS, but much more. We call this a virtual sensor. What it means, virtual sensor? We take a physical sensor, like a microphone, and now you have the ability to speak to the machine, and the machine can understand you. So we have an AI sensor inside. So it's not only a microphone, it's microphone with AI. So together, you have a very sophisticated sensor, because right now, it can understand you. For example, in the example of Moshe, he wants that the robots make 85 degree. So if you don't say 85 degrees, you, for instance, say 85 centimeter, so the system asks you, are you sure? Because she knows to connect the scalar information with the units.
Yeah, Ofer, I think the question was different, and let me give an answer and tell me if I'm right. Both LabVIEW and the smartphone have standard interfaces to other instruments. So let's suppose you want to connect a radar to your robot. That's certainly not part of a smartphone. So if the radar has an output port, either
yes, we have
something which is standard like a USB, or something which is
like database. We look at the database as a switch. We look at the database as a switch, and through the database, you can handle everything because we are an IoT device. So we can handle actually everything.
Right. So the basic concept is that you have a platform which is intended to use data from anything. So as soon as the sensor that you introduce has a way to output information, then if it's Bluetooth, you can do it through the phone. If it's Wi-Fi, you can do it through the phone. But if it's something different, you may need to buy some interface instrument to translate to a format the system can read. But as a matter of principle, this is an open system which is intended to be IoT. So it's intended to integrate any data generating device of any kind into the data. And the system would be, you tell the system what the data is, how to use it, and you tell the instrument how to output the data.
Got it. Okay, Cool.
And so the standard Android phone, can you just summarize the sensors that the phone itself has? I know there's the accelerometer, there's the gyro, there's the GPS, obviously a microphone. What other sensors are embedded in the Android?
Well, it measures temperature.
Camera, of
So
course.
again, you have to remember that the phone, almost by definition, have sensors of a given accuracy.
Right.
So the camera is actually wonderful. The microphone is mediocre. And the temperature sensing is also mediocre. So depending on the project that you want to do, you can do a lot with a smartphone alone, because the gyro it has is very sophisticated. It would measure both the orientation of the phone and acceleration. So acceleration both linear in 3 dimensions, but also rotation in 3 dimensions.
Mm-hmm.
So everything to do with movement, the smartphone will provide you with some accuracy. You may want to do something much more accurate, and then you have to buy an external device and connect it, which you can. But if you want to, you can do a lot staying within the sensor of the phone. It has temperature sensors. It senses the direction. By the way, it has not just a gyroscope, but you can figure out where the true north is.
Compass.
Compass, right.
Yeah.
But much more.
Mhm.
Like if you're talking about the camera. So you have the camera in the smartphone, but we have a lot of sensor through the camera. For an instant, like face recognition.
Right.
But it's not only face recognition, because it's also measure the distance, and it measure the X and the Y and the Z, and you have a lot of dimension that is measured for you. So if you want to build, for an instant, a control system that you move your head and the robots go after you, after your face. And if I do something like this, it go down and go up and all these things. So you have in the sensor that we built, the virtual sensor, you have all the measurement also, not only the recognition of the face of the special person, until 5 persons that you can recognize together, you have also the measurement. This is very important to make a control system.
And then just
So,
go ahead.
let me explain this for a minute, because there's a very basic principle that is hidden in what Ofer is saying. So if you have a camera, you can ask any second-year computer scientist to figure out from the camera how to do face recognition and the direction the person is looking at. What Ofer is doing is building a modular system. So once there is a module that does that, any students from high school, from middle school, from elementary school can be taught to use this technology. And so now the student can build a system that looks at you and see where you're looking and does something as a consequence, because it was already built. If you want to challenge the students, you can say, okay, you can't use this model, build your own. But the system is growing all the time with new abilities that you connect as modules, which you can do because it's all on a computer.
No, that's helpful. So thank you. For the example of the control system, just so I can understand it, the camera acts as a sensor. That data gets transmitted to a laptop or a desktop. And in the control system algorithm, is the processing then done in the cloud, or is it done on that laptop or desktop?
You have 4 processors that work together. 1 work in the computer,
Okay.
1 work in the smartphone, 1 in the cloud, and 1 in the robot. And is also a different operation system, because on the computer we run over Windows 10.
Okay.
With the robot we run over Ubuntu. It's a Linux system.
Mm-hmm.
In the smartphone we run over the the Android operation system. And in the cloud, most of the thing we write in a web class in Python.
Okay.
So the AI things, we need power. So and to run the deep learning, we handle a lot of things with deep learning. So it takes time and to work with the system. So you need the cloud, but the system himself know how to handle the processor. So it must to work in a real time. So it's give you the best solution for the runtime. So the process, he understand what is the mission and how to divide the work between the processor. So in dynamic is very serious system because it's not simple to handle 4 processors synchronized together to do a dynamic job.
And two specific questions, and then we can, maybe chat more about the system and the process and things. But when I would be interfacing with, I'm gonna call it the system, so I want to measure the temperature in this room as an example. Is my main interface with my laptop desktop, using Windows, or is it with, quote, the computer on the robot that's holding the phone? So,
Yeah.
so which,
We have a two method.
okay,
We have a method, it's called interpreter, and they have a method, it's called compiler.
okay,
Sometimes you don't want the computer anymore. You want the computer only to do the edit and maybe to do the debug mode. But you built a system and you want it independent without any computer at all. So then you have only three processors. The process of the Windows is download the software to one of we call this the brick. This is the main system. And he knows to distribute the job between the cloud and the smartphone together. So he knows when I send the order, the commands. So if he see that this command is to him, so he's run it in this processor with the Ubuntu. If it sees it is something, the sensor is in the smartphone, so he say, okay, he is communicating with the smartphone in a Bluetooth. So he send the order, the command, and the smartphone execute, and then replace the answer to the main processor. If it see that it's something is with the cloud, so like the AI commands, so we stream the audio or the video to the cloud, analyze everything in the cloud, in real time, is give you back the data that he analyzed. So you not have a lot of data when he analyze, because how much data you need, your name, to recognize your name, compared to the streaming of the video that you send to the cloud.
right.
So, and much more if you have a sensor that is an IoT device. For instance, this is the sensor that you want to see from the electrical company.
Yeah.
So through the Firebase, that is the database, we look at the database like as a switch. So you can measure something from the cloud, through the cloud to the database, from the database is go to the smartphone, from the smartphone to the main controller. So they have a topology.
But the student and
To him it's transparent. Everything,
Yeah,
what they say is
right,
transparent.
Right.
They
No, that's
interface
the beauty.
with a system on the computer, on their own computer.
If you want to work with interpreter mode, in a debug mode, for instance, so you work with the computer, with the lab view, and on the lab view in real time, you can see all the details that you want, all the parameters. You go with the mouse, look at the place, and you see what is the real data. In the same time, I can show you some example, but
Yeah, no, I think we get the understanding of it. Let me do my last question. If I wanted to do the classic inverted pendulum, experiment.
Yeah,
Okay.
we love this experiment.
I'm not surprised. Can you just
The resonance together.
right? Can you just walk me through where the calculations are done for that control system for the inverted pendulum?
Okay, we have two methods. One method is we call offline. What does mean offline? You say, okay, for the pendulum, I need the gravity because I want the angle. Then I want the velocity. So I say, okay, I need the gyro. So I have the angle velocity, and I need the accelerometer to measure the accelerator. So you say, okay, I need this sensor, this sensor, this sensor. I need it in 100 hertz, and the measure of the time is 20 seconds. That's all. You pick up, the sensor like this, something very simple way, very, very simple way. So in one order, he make everything for you. All the data information, the data collection, everything by himself, and then he built you a file, CSV file. So comma separate value. You have all the value that you need. If you want to work with MATLAB, for instance, sometimes we prefer to work with MATLAB. So you work in offline with all the data that you collect, work with MATLAB. We give you another tools like MATLAB, so cool, because for the pendulum, we know what we're supposed to show, so we have a regression command. And it's like in the Excel, you say, okay, what is a polynomial or sinus or whatever is that you help him to the system, and he make the regression, and he give you a formula that's present all the data that you bring you. So we have all what you want. If you want to work offline or online, whatever you prefer.
So, this is just really helpful and informative. If I could pause for a minute and just share the thoughts of why we're having the call and where this might be useful is, it's amazing the technology that you have, and I'm also amazed that neither Larry or I have heard of it as an integrated system. And what we're contemplating is how do we make use of that within the Yale environment here, and also within the community. We're in Connecticut. Is there some platform that can be used within influencing Connecticut and beyond? But one of the thoughts is copying the work that you've done at Technion of using this to draw people into the university, into the institute. And is there a way for us to make use of the work that you've done, given all due credit to Technion, but use it as a national recruiting program for top science and engineering students, so that we offer them this ability to learn? In this case, I'm limited to physics fundamentals, and they're doing this in addition to their normal classroom work. And then obviously it has the project component, much like the projects that you've done and used at the Technion. And then students would compete, for the prizes are minimal. It's really just the awareness. But at the center of that is Yale, 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 right?
Right.
Like, oh, this is the Yale Technion program, or whatever we would call it, but we draw attention, and maybe a partnership of Yale and Technion is the way to go here, because we don't want to pretend that we invented this, and there's strength in collaboration. So let's just extend that for a little bit, that this is a Yale Technion program on physics awareness done on, I can speak nationally, right? If we want to make it international, that's a different story. But it provides this opportunity for students to learn in addition to their curriculum. And why am I careful with that? is because, you know, we can't control what gets done at an individual high school. We're very, very, very much about access and opportunity. So to give access and opportunity to specific students in, you know, high population density areas, areas that we may want to recruit from for one reason or another, you know, we're not going to have people there, but I think what we've learned over the last 18 months is with the right resources, you can be very, very effective in this way that we're corresponding now, communicating right now. But it really has to be augmented with hardware that people have at their hands. It can't just all be this. And Larry and I taught the course last semester, and we'll do it again this semester, where, and we've done this, product development, people take sensors and they make simple devices. And we did it throughout the pandemic. And people were remote, people were in person, but without that hardware interface, it doesn't have that sense of reality. The other thing is that project-based, so we're all, you know, you're getting your theory, you're learning your theory, you're learning more of the theory because you have access to these tools, and then there's a culminating project, which, as you know, it puts everything together and it gets that sort of sense of excitement. So that's a little bit of just the preliminary thoughts of, and all of this would be done in partnership and agreement with you, right? It's not like, oh, we're going to run with this. So that explains a little bit of the current thought of using it here at Yale, of what, why, how, we could tap into your work and then share it with a different audience. So,
let me comment on that.
Okay.
And I understand that you're familiar with FIRST quite well. So,
and Larry as well.
Right. So actually, FIRST was brought to Israel by a person who is now the vice president for resource development, Alon Wolf, and he runs the program in Israel. Israel has one of the largest groups that go to the United States every year. It's very popular in Israel.
Yeah.
And I think there are some shared principles here. One is that kids really like to do things, and that motivates them to learn. And they're willing to work very, very hard when they have something which is an exciting project that looks connected to reality. And it's a wonderful way to get people interested in science and in technology. So we have been using Offers project at a lot of levels, starting with just making sure that more kids are interested in science and technology. And we find, for example, that school principals, in many cases, grab this like a gold mine, because for them, they know that the students are going to be enthusiastic about it, the parents are going to be enthusiastic about it, and it's affordable. It doesn't require them to buy the kind of equipment used for FIRST, which is quite expensive, and it involves more of their teachers, because the expertise required beyond the science that they know is not very much. You have to take some courses to understand how technology works, and what is not less important, you have to learn what the philosophy is, because there is something behind this. So it's very effective to get kids at any age to be interested in science and technology and drive them to learn more, both theoretically, but also do a project. It's an affordable project. It gets the teachers very interested, because teachers like to do projects. Once they get over the barrier of understanding that they can do a project that they don't know all the answers a priori, and Ofer has some wonderful stories how students together with a teacher, for example, were trying to figure out how is it that the leopard can turn so quickly when they run so fast. That was a question that the teacher did not know the answer for, and they could not find it in Google. And there was a research project of a group of kids with a teacher until they found the solution, implemented, and proved that this really works. You can build a robot that behaves like one of these animals. You can prepare students for an institute like Yale, where you want students to come with more understanding and of concepts that are not taught in high school. And we use that in electrical engineering. So sometimes we cater to the whole class just to get everybody interested. Sometimes we cater to the brilliant students in school to get the top that is a potential student for our electrical engineering department, for example. And you can tailor the program to whatever you want and be effective in all. One of the things which I think is really important is that there are some engineering concepts that you learn in this program which are not taught in schools and usually not even in universities. Sometimes in physics department they are. But the idea that what you measure is not perfect and you have to figure out where the errors come from and minimize them, and all these things that engineers do all the time and physicists, experimental physicists do all the time. The experiments you do in high school with the standard equipment are verification experiments where you try to prove that F equals MA is true. And you try to be perfect. And in here, because the data is so large in quantity, you're able to show people that there are measurement errors, there is noise, there are a lot of things that happen in real life which are really important, they are part of science, and you have to understand them. So there are some concepts which are very hard to teach you in standard methods, and here come naturally as part of the education. So to summarize, you can build programs to different kind of audience. This program is scalable. I think any school in the United States has the resources to get what they need to run the program. It's not an expensive program.
Right.
They're willing to devote the time and the effort. And you can build excellence programs which are supervised by Yale in the same way that Technion supervises these advanced projects. So in the Technion, in order to do an advanced project, you need to get a staff member from the electrical engineering department to both check that the project is of the right scale, and then do the midterm and the final test. So we are involved personally because we want to make sure that the level is the same as of our students. But this is just a program for the top people. There is also a program for any student that you want to get interested. So you have to decide what you want. The nice thing about this system, it's very general. It can do any level that you want. And in terms of a Technion, I can't speak to a Technion, but my feeling is that if you call a Technion and ask to collaborate, they'll be more than happy.
Yeah. Larry, do you have a question or two? I want to get something, but I'm just going to step off camera. But
yeah, sure.
Go ahead. I am here.
Can you say a little more specifically what equipment you would need to do a project or a fairly simple project? I mean, I understand there's a phone, but could it be any phone? And
smartphone and a Lego is be fair enough. Smartphone and Lego EV3 be fair enough.
So does it have to be an iPhone or an Android phone, or
Android,
and does it have to be
Android phone? Android
an
phone.
Android phone? And then the hardware component, the part that you said runs Ubuntu, the like a Raspberry Pi or whatever, is that a separate thing that you purchase?
No, I use with the processor in the robot himself. So the Lego EV3 for us is also the controller.
Oh, so when you say
you have
Lego,
four
you mean
controllers, like I said. Lego EV3 is one of the controller.
Okay, so it's the actual
Yeah,
Lego.
Larry, hold on for a second. Let me separate things for you, because Ofer is thinking of the projects that he's doing with the students. And again, this system is very modular. So right at the beginning, the concept was you take an Android phone and you turn it into a measurement device. Now, if you want to show the students what happens with acceleration, you take a little cart with wheels and you put the phone in it and you let it measure, and that's all you need.
Okay.
If you want to build a robot, you need the parts that make a robot. And what Ofer is using right now is something that is a toy for kids, made by Lego. and it has a heart, which is a processor with a certain operating system and a language, and the ability to integrate both sensors, but also output commands to motors that will activate the robot. And then you buy the physical robot, which is made by Lego, and you can build a robot. So it depends what you want to build. If you were to decide that you want to do something really sophisticated and spend $100,000 to buy an industrial grade robot, it will probably take over a week to create the interface so you can do something with that robot. Because the system can deal with anything. If you want to do something basic in school, I'll ask Ofer to describe what a typical school purchases in order to be able to run projects. So go ahead, Ofer.
For example, if I can show you only some of the project that we make with the Lego.
Ofer, they saw all the project, they saw all the video.
Okay.
He asked what is the equipment that they need to.
You saw the Cheetah project for an instant. You see,
yes, all the project, all the video. Great. They just ask about what the school need, what component, what parts. So,
that's what I say. To us, it's enough if you want to make a really nice project, a serious project. It's look that the Lego is a toys, but the Lego EV3 with RoboPhysics is not a toy at all. You can do a really serious things with this toy, so-called toy.
Larry, you need EV3 computer and cell phone.
Got it. Okay. Let me come back to the thing you asked about FIRST. I've co-authored 3 books on FIRST. Mm-hmm. And so Larry and I both helped the national organization, the international organization. Does the name Josh Weston ring a bell? Josh Weston at all?
Yeah.
Okay. So he's a friend, and actually I visited Israel February 2020 with Josh and 15 others, and we did a series of visits around the country in 5 days. So, and the founder, Dean Kamen, is a very good friend. So, and I'm the treasurer of the FIRST board. So everything that we would do would only be complementary, not competition to FIRST. And they are very, very different, as you said.
Yes.
So, and where I'm excited about this is that FIRST is more application based. I'm going to be very general. And the work that you've done with the projects at the Technion is more, I'll just say physics foundations based, formula based, right? Analysis based. That is not FIRST, right? So they have different aspects, but they're very much in line with how that learning takes place. So that's where the excitement is. I'm just thinking for us. So let me explain. I explained the Yale project. 2 other things that contemplating that quote I can think about and try to implement is a community-based instruction sort of after-school project on how to learn the fundamentals through a guided curriculum, which I know RoboPhysics has, which is very, very appealing, the curriculum aspect of it. And then the second is integration within a school system, within a physics school system. So let me talk about both of those. The after-school curriculum is complicated because of COVID right now, and so we don't know, will locally will people go ahead and assemble? But the thought is within a community, and it's communities that we're established in, either the community I live in or within the New Haven community as an after-school program, to get a group of students that would march through the curriculum and then have the project, so that we would gain some local familiarity. That's one idea. The second, and it's actually independent of COVID, is taking the curriculum into a public school is very difficult because of the science standards that have to be met, and the teachers don't really have that much autonomy. However, within a private school, it can be done very easily. So I've approached a teacher in a private school, applied physics, and he's very, very interested. So he's a physics educator, former Coast Guard officer that I know very, very well, lives in our community. And so there's an interest, preliminary interest, to do it within physics. But, we're in August 18th, and classes start in 2 weeks. So I'm like, well, just sort of sense of time. But that's the 3 levels. To introduce it into a private high school physics program, to do a community-based education project, and then to incorporate it as a much larger Yale Technion partnership that draws attention to the top students of the universities. So that's it from this end.
Who would be the staff in the after school program?
What it would be is administrators within that program. So each of them has someone that's appointed that runs the program. And what I'm thinking is to develop the curriculum, which would not be in the administrator's purview, is that we would tap into high school students. So let me back off for a little bit. The community-based program wouldn't be the same level as the cheetah or the leopard. It would be down a level. But we'd use the high school physics students to be the educators in implementing that, say, a middle school program. So that's the thought for that one. For the high school, it's the high school teacher. And then for the university program, it's quote, us here at the university. So those are the thoughts.
Is it feasible for you to to take students from the university and put them in a position of educators? Is that something you do?
So yes, but not for educational credit, just for public awareness. Yeah. Of course. Yeah. So they would, much like the first program, they're mentors on the first teams.
Right.
And this in essence, they'd be physics mentors. So.
Yeah. So we have experience with students supervising projects. I don't think we have experience of high school students supervising lower level students. I don't know. But certainly anybody involved will have to go to go through some program to teach them how not only how to use things, but how to teach all that stuff.
Correct. Yeah. So the model here that I'm basing on is on Physics Olympics, which is a international competition, and then the high school students contribute to that under the leadership of quote a physicist, a practicing engineer. Yeah. So fully aware that we can't just drop people in and say, okay, go get it. And that brings us to the one question, if I spoke with Mochi, that I really think that who knows how long this pandemic is going to be with us. So therefore we need to be thinking, how do we train the trainers using the remote education tools? So so I think Ofer went through at least one session of this kind. Certainly not optimal, but sorry, but it's possible. Just one side comment, which is a little more long range. In Israel, the person who is in charge nationally of physics education, also in charge, of course, of all the curriculum taught, became very enthusiastic about this program at a very early stage. And we are in exactly the opposite position, where the public schools can get credit from the regulators and some resources also to run the program. So they'll actually get teaching hours, additional teaching hours, so they can run the program in school. And the bottleneck is that we just have one offer and he can't expand fast enough. But it actually happened at the national level, not only in private schools. So that's good.
But that's long range.
Vince, I think we talk about this. If it will be possible, we will run it, the first teacher training to train your people. It depends on the pandemic. When we finalize all the details, we will find solution, and the offer already run teacher training in Israel a few times, and the teacher get credit of a point. I don't know if he's in the state. So he have full curriculum for teacher training.
Okay.
So it's not new for us in Israel. You already do it in Israel many times.
Good. All right. Well, this is really, really helpful, and I, commend you for the work and the thoroughness. I think at this point, Moshe and I are speaking. We can continue to, put together some plans. Larry and I will think, maybe there's a way for he and I to, begin to look at the technology closer, to actually use it ourselves, so we have a little bit more familiarity with it. But I'll connect with, resources that we might need and details from our end. So.
Yeah,
Okay.
this looks really exciting, and looking forward to, as Vince just said, a first step is for us to kind of get a hands on it and have a better understanding of what we could do with it in other contexts.
Excellent. Okay.
Okay.